Leetcode and finding a job in this market is hard. As an engineer and someone who was also binging a lot of these coding channels, I noticed that even after watching the video explaining the problem, sure, I knew the answer, but I couldn't really visualize it or fully understand what was going on. Some concepts were just hard to portray from drawing on a screen alone, so I figured I'd start this channel to help visualize some of these problems with animations. Right now, this is you, but don't worry, you'll be cooking soon. Today, I wanted to go over a dynamic programming problem, specifically Leetcode 474. There's different ways to solve it, but I'm just going to cover the one that I believe is the easiest to visualize. The basis of the problem is simple. You're given an array of strings, which are numbers that only contain ones and zeros. You're also given values for m and n. The question is, what is the longest subset that I can create from this array in which there is no more than m ones and n zeros in that subset? So I set up this binary tree to kind of help visualize all the possible paths here and the subset that would result from each path. In this case, for the example array of 10, 0, 1, the optimal solution here would be a subset of 0 and 1 with a length of 2. Any subsets that have more than 1, 0 or more than 1, 1 can be ignored. So as you can imagine, brute forcing this problem would not be efficient because there's just too many possible paths that you could take. So that's where dynamic programming and caching comes into play. By caching, we will avoid doing repeat work and instead build upon what we already know from iterating. Let's consider the following example array of 10, 0, 1. Let's also say that m is equal to 1 and n is equal to 1, meaning you can only have up to 1, 1 and 1, 0 in the resulting subset. We're going to cache the information we know so far in a dictionary called DP. For the key, it's a tuple where the first index is the number of zeros in that subset and the second index is the number of ones in that subset. The value is the max length of that subset for that amount of ones and zeros. Each entry in DP represents a possible path that satisfies the constraints. The way this will work is for each element in the given array, we will iterate through all of the info stored in DP to see if we can add that element to each path. Let's start with the first element of 10. We then check every entry in DP and ask, can 10 be added to this path? Since we can add it, we've created a new path. And this info should be added to DP with the updated amount of ones and zeros, as well as the updated subset length, which increases by 1. Moving on to the next element of 0, can it be added to the first element in DP? In this case, it can. However, we can't update DP right away because we're currently iterating through it. So we need to store all of the updates in a separate dictionary called newDP. What about this path? Can 0 be added? No, because that would mean we have 2 ones in our subset. So we don't care about that path and don't need to cache it. Now that we've iterated through all of DP, we can then update DP with the entries in newDP. For the last element of 1, we can continue the same process. However, we come across an issue when we add the element to the last path in DP. There's already an existing path in DP with 1, 0 and 1, 1. So in this case, we need to compare the subset length between the two. If the new path has a greater subset length than the one we already saw, then we use the subset length of the new path. If it doesn't have a greater subset length, then it doesn't need to be cached. After all the elements in the example array have been iterated through, we can then simply return the max of all values in DP. Now for the actual code. We first initialize our DP. We then start iterating through each element in the array and obtain the numbers of ones and zeros for that element using count. Before iterating through DP, we initialize our new DP. Now we start iterating through each entry in DP. We then check, can we add s to this current path? Or in other words, does the number of zeros and ones we've already seen plus the number of zeros and ones in s satisfy the constraints? If it does, and adding that element results in a new path that isn't already in DP, we add it to the new DP. However, if adding this element results in a path we've already seen, and the subset length of the path we've already seen is less than the subset length of this new path, then add it to new DP. You might be wondering, why not just put that if and else if statement into one or clause, since they're doing the same thing? Well, if we did that, it would throw an index error in cases where a path is not in DP yet. so we don't want to call that key in DP unless it's actually in there. So keeping these clauses separate avoids this issue. Finally, we update DP with the entries in new DP and return the max of all values in DP. So hopefully after this video you have a clear understanding of this solution. This problem was not very complex, to be honest, and I'm interested in making some animations on some harder stuff, so stay tuned, and thanks for watching.